9.81, and then I would find my weight, and that would be my weight in newtons, not my weight in pounds. Our weight in newtons is going to be a lot more, unfortunately, than our weight in pounds. So gravitational force is always going to be directed toward the center of Earth, so for us it's always just directed downward, and it's going to be due to the acceleration due to gravity. So we can apply Newton's second law to just one system, a part of a system, or the whole system. And how you approach a problem is solely going to depend on whether you apply it to part of the system or to the entire system. And it's fine if you do one or the other, and in a lot of cases you can choose, a lot of cases one will be easier to do than another. But you need to make sure that you're applying all of the forces on just that one particular object. So for example, let's say this is my overall system. I have mass 1, block 1, and block 2 over here. They're attached by some type of rope or string, and there's an applied force that's being applied to mass 1, and it's telling me that the acceleration is going to be in the direction of this applied force, okay? So maybe I ask you to draw just a part of, or a free body diagram for only mass 2. I want you to draw a free body diagram only for mass 2. If I did that, and this free body diagram is actually missing a couple of forces, so let's add that, okay? So mass 2, it has only the tension force on it, because this is a contact force. That's only applied to mass number 1. It's not being applied to mass number 2. The only reason that I'm feeling this force is due to the tension in the string that's pulling mass 2 along with mass number 1, okay? So the only forces that would be acting on mass 2, that one doesn't work. Guys, my technology is broken today. Okay, I got another one, don't worry. Because I know you were. Okay, so mass 2. I'll just draw the situation again. Here's M2. Here's M1. Here's the applied force. And this is my overall acceleration. So I have tension in rope here, tension, all that good stuff. So I just want to draw a free body diagram for mass 2. When you draw a free body diagram, we're going to represent the object as a particle, okay? So instead of actually drawing the object, it's just much easier. And then all of the forces are going to originate from this particle. So I know that mass number 2 has a weight force. It has to have weight, and weight force is directed down. So I'm going to call that F sub G. Or you could call it W for the weight force. Either one is fine. Sometimes you'll see a vector that's specifically for weight, and it will say mg next to it. And the reason that it says mg next to it is because weight is equal to the mass times that acceleration due to gravity. So you may see them either way, and that's totally fine. So in this case, let's just call it F sub g. I also know that it's on some surface. So if there's a weight force that's pushing on the surface is also pushing up on the wooden block. So I have the normal force that would be directed upward, and these two should be equal to one another, and they should be equal because it tells me that my acceleration is in a horizontal direction. It's not in a vertical direction. So since it's not accelerating vertically, these two must be equal, okay? Now the only other force that I have acting on it in the horizontal direction is tension. So I'm going to have a tension force, which we can just label as a capital T, moving toward the right, okay? So that would be for mass 2. If I want to do the same thing for mass 1, I'm going to look very similar. Mass 1 has a weight force. Mass 1 has a normal force. Those should still be equal. Those don't necessarily look equal. I have the applied force that's coming off this way. So we'll just call that F. Actually, let's call that F applied because that just means that it's the applied force. Okay. And then I also have tension. And tension is going to be directed in this direction because ultimately I have to pull mass 2 with me. So tension is going to be that direction. So tension's there. So that was mass 2, this was mass 1. So those would be my free body diagrams for the both of those wooden blocks, okay? Normal force. So we've talked about normal force, but let's actually give it a definition. So a normal force is the force that a surface exerts on an object, and it is always perpendicular to the surface. It is a reaction force. So the normal force is the force that a surface exerts on an object, and it is always perpendicular to the surface, okay? And again, we consider it to be a reaction force. The reason that we consider it to be a reaction force is because typically what will happen is an object is resting on something, it's resting on a surface, and it has weight. It has some type of gravitational force that will be pulling it down. If I have a book that's sitting on a desk, the desk doesn't want to break, so the desk is going to push back up on the book in response to the book's weight. So we think about the normal force as being a reaction force. It is the surface's way to react to whatever force is being applied on it. So normal force is always perpendicular to the surface. Okay, so if we have, this is a very, very, very easy question. I have a tractor pulls a loaded wagon on a level road with a constant horizontal force of 440 newtons. If the mass of the wagon is 200 kilograms and that of the load is 75 kilograms, what is the magnitude of the wagon's acceleration? Let's assume that there's no friction. Let's assume that we are on Earth. And ultimately, I know that this is just a Newton's second law question. I have a force, and this force is 440 newtons. They tell me that. And that 440 newtons is pulling the 200 kilogram wagon plus the 75 kilogram load that's in the wagon. And I want to know what the acceleration is. So the net force is equal to mass times acceleration. So that means 440 newtons is equal to the total mass, which would be 275 kilograms times A, times acceleration. So you could set that up, and you should be able to find that the acceleration is equal to what? Should be equal to 440 divided by 275, and what? That's 1.6. So it should be 1.6 meters per second squared. That would be my answer. Okay, let's go to another easy baby question. Let's say that a student weighs 588 newtons. What is her mass in kilograms? So we know that weight is just a force. So I know force is equal to mass times acceleration. The force is 588 newtons. And if it's her weight, I already know the acceleration due to gravity, and that's 9.81 meters per second squared. So I'm going to take 588 newtons divided by 9.8, and then I'm going to get her mass. That would be about 60 kilograms. So her mass in kilograms is 60. And then if you want to convert that mass from kilograms to pounds, in every 1 kilogram, there's 2.2 pounds. So if we know that her mass is 60 kilograms, I can just take that times 2.2 to get how many pounds she is, because in 1 kilogram, there's 2.2 pounds. So if I did 60 times 2.2, that's 132 pounds. So then she'd be at 588 newtons. That would be equivalent to 60 kilograms, which would be equivalent to 132 pounds. So if you wanted to find your own weight, take how much you weigh in pounds, divide it by 2.2, and that will be your mass in kilograms. And then take your mass in kilograms and multiply it by 9.8, and that would tell you what your weight would be in newtons. Okay, so the free body diagram, which we already, again, have done, so I'm just going to go through that really quick. In a free body diagram, we are only showing the forces that are acting on one particular object. And we want to model that object as a particle. So if I have a computer sitting on a desk, then I am only wanting to think about what forces are acting on the computer, on that monitor. So I have the weight of the desk, or the weight of the monitor that's pushing on the desk, so that's the weight force, so that would be F sub G. And then I have the desk pushing up on the monitor, and that's the normal force because that is the surface that is pushing on the object perpendicularly. So that would be my normal force there. So I'm just going to represent them as vectors with arrows and then label them, and we will be perfect. So every problem that you draw from this point on, you should have a free body diagram. There is no way on earth that you can do a problem on any part of your AP test that is a force problem without a free body. They will look for this. So free body diagrams are the easiest way that we can get points or show work on an FRQ. So free body diagrams, I will call them FBDs from this point on. And if you don't have an FBD on your paper when you come to ask me a question, I will not respond to you. You have to have a free body diagram. Okay, so let's say you have this huge, crazy system like you have right here. This is a really big, beastie one. I would break it up into pieces. Remember that we can only just look at one object at a time with a free body diagram, and that's exactly what I would do. If you have a system that has several masses in it, look at just one object, okay? So for example, if you can see this one here, I have a box that's attached to a string, and this is a pulley. So I have mass 1, it's attached to a string, which is attached to mass 2. This is called an Atwood's machine. Mass 1 attached to mass 2, and they're connected by a string over a pulley. That's an Atwood's machine. But it makes it even more difficult because look, this mass 1 is on an incline. So anytime we include inclines, it makes it so much more difficult. But let's look at this one. Okay, so here is my incline. Here's theta. And here's mass 1. Here's the pulley. Here's mass 2. Okay? Okay. Looks like a pretty good system here. Okay, so let's just do mass 2 first, because I think that mass 2 will be significantly easier to do than mass number 1, all right? If we're looking at mass 2, I'm asking you, what are the forces that are acting on mass 2? So mass 2 has a weight force, of course, so I'm going to represent mass 2, and I'm just going to call M2 over here to label it. Mass 2 has a weight force. We know it has a weight, so we're going to call that F sub G. And then the only other thing that's acting on mass 2, other than just having its weight force, is going to be tension. Okay, so tension is, could call it F sub T for force of tension, or let's actually just call it a capital T for tension. So I have tension directed upward, I have the weight force pulling it down. So that would be my free body diagram for mass 2. Easy enough. Mass 1 is going to be more difficult. So here's my mass number 1. I'm representing it as a particle, remember. Let's talk about all of the forces that are acting on it. It's on an incline, which makes this even more difficult. First of all, let's always go weight force, because we know that the weight force is always acting on any mass.